Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Last time we derived this rocket equation right here. Today we're going to understand it, and then we're going to use it in two examples. One in a space where external force is zero, and the other one in the surface of the Earth when the external force is going to be gravitational force. So let's start! Great! Now let's try to understand this equation right here that we derived last time. We can see that we have a component of external force that is being applied to all of the rocket. And we have this is positive and this is going to be negative. Therefore, if we take this to the other side, we're going to get that F external it's going plus the change in mass of the rocket and the velocity of u equals the mass of the rocket times the velocity, the acceleration of the rocket in on itself. Note that it is true that the velocity of the fuel points down. However, the rate of change of the mass of the rocket also is negative. Therefore, this is going to be a vector pointing upwards. It's going to be a force pointing upwards. And this force, we don't know its direction because it is external. But therefore, we see we're going to have an external force that is going to be this one right here. And we can consider this component as a thrust force. Thrust. I believe it's written in that way. And in here, we are going to have the mass of the rocket times its acceleration. So we can see that what this equation has given us is that this component right here, this thing, is no other thing than a thrust force that supplies to the rocket some acceleration. And that is what we'll learn from the rocket equation. Let's express it in components so that we understand what happens really. We're going to have this external force, let's take it to be gravity, for example, and therefore if we select our j hat vector to be upwards, we're going to have a minus mg j hat. The blue pen is not working too much anymore. And this thrust force is going to be plus dm dr, so this is going to be a negative quantity, and we are going to have a minus u times j hat. And in here, we are going to have an acceleration in the j hat. And sorry about that, but this should be a vector earlier. Therefore, we see that actually this is pointing down, but like we said before, our mass is going to be decreasing. Therefore, this derivative is negative, and it is going to be a force that is going to supply positive acceleration to our rocket. And this is the rocket equation. Great! Now we are ready to start solving some exercises. Let's first consider the case in which the external force is zero. We're going to have our rocket at time t, and it is going to have a velocity v of r and a mass mr time t. And then at time t plus delta t, our rocket will have moved a little bit, and we're going to have minus delta mr of mass over here, which is going to be positive because that increment is negative, and the mass of this is going to be m of r plus delta mr, and the velocity is going to be v of r of t plus delta t. It's going to have changed. Great. We already knew that from the last video on the rocket equation, but it's a well practice to set up our system like this before we start trying to solve everything, so that we know what each of these quantities really mean. Now let's try to work with that equation. Recall we are saying that our external force is going to be 0. Therefore we are going to have dmr over dt times u equals mr times dbr dt. We see that those dt's can be cancelled, and we can easily solve this by separation of variables. We need to get the mr to the other side, and we get dmr over mr times u equals db of r. Now, if we do some integrals, we see we get the integral from mr ti to mr of t times dmr mr. Let's put primes in these ones to differentiate between the dummy variables and the limits, times u. And on the other side, we're going to have from b of t initial, b of t times dbr prime. If we solve this, we see that we get a logarithm of mr of t over mr of ti times u equals this thing, that is b of t minus b of ti. However, note that our mass is going to be decreasing, therefore this logarithm is going to be negative. We can put that more explicitly if we solve for b of t and we put a negative sign by exchanging these two coefficients, or just getting a minus 1 in front and putting a minus 1 as an exponent inside, which is actually the same. Therefore, we get that our velocity b of t equals b of the time initial minus the logarithm of mr of ti over mr of t. Note once again that this velocity points in the opposite direction. This velocity points in this direction because this is b fuel and this is the relative velocity of the fuel with respect to the rocket. Therefore, this is going to add another negative sign, which is going to cancel this one over here, and the velocity is going to be higher at a later time than at an initial time. And this is an example of how to use the rocket equation. Great, now let's try and solve the problem when the external force is non-zero. Imagine we are in our rocket and we are near the surface of the Earth. Therefore, there is going to be a gravitational acceleration mg. We are going to have this vector and we're going to have our j hat vector. This is the mass of the rocket. Alright, in our j hat direction, and we're going to do this just with the components because it will be much easier, we're going to have minus mg as gravity is pointing downwards. Then we're going to have minus u as the relative velocity of the fuel with respect to the rocket is going to point downwards. So it's going to be minus dmr dt u and we're going to have that is going to be positive because we have BR positive, MR dBr dt, and no vectors because we are just only treating components here. Alright, now let's establish what our initial and final conditions will be. We're going to have time initial equal to 0, a time in which the mass of our rocket is going to be equal to the mass of the container plus the mass of the fuel, and the velocity of the rocket is going to be equal to 0. This is going to be our initial conditions, and we are going to try to find the situation of our final state at TF. In this case, we're going to find the state in which the mass of the rocket is only the mass of the container. That is, we have used up all of our fuel, and BR is just going to be dependent on the time, the final time, the total time in which our rocket has been propelling material. Great. Now we are ready to confront this equation. It's a little bit harder than last time, but not too much. Recall, we are talking specifically about the rocket. The rocket is our system. Therefore, the mass that gravity is affecting to is the mass of the rocket. Now let's divide by the mass of the rocket to get it with its differential, and let's multiply by the time differential. We will get that this is minus g dt minus dmr u equals dbr. Now we are ready to take some integrals, and we are going to take 3 separate integrals. Let's put this as a plus, and let's put the minus in here so that everything is clearer probably. And we are going to take this from time equals 0 to time equals tf, as we said before. We are going to take the mass from being initial mz plus mf, m fuel, to be m of the container only. That's the final mass. And we are going to take our velocity to be from 0 to final. Let's prime that to differentiate between the different variables we get. Now, these integrals can be straightforwardly solved, and we get minus g times t final minus, this is a logarithm, so recall we're going to have mz on top, and the minus will become an mc plus mf in here. If we obvious this part, this is the same thing we had before, just with mz and mf instead of initial and final masses. Times u. It's important to remember this factor. And we're going to have on this side just br of t final. Now, to clarify this, let's put this minus inside of this quantity, because actually the logarithm up to here it's negative. So this will work. We're going to have that br of tf equals, we swap the fraction and we get the logarithm of 1 plus mf over mc times u minus gravity times t final. So we indeed see that this component helps the velocity go up, the thrust helps the velocity go up, and the gravity opposites this growth of velocity. And this is how you solve a system, a rocket problem, in which the external force is non-zero. That is all for today. I hope this video helped you clarify your understanding about the rocket equation and also helped you understand how you need to apply it when dealing with external forces or when external force is zero and all different cases. Furthermore, I hope you understood the analysis that we have taken to find this rocket equation, because it will be very useful in other physical problems you will confront. Any doubts left, you may ask them in the comments section. Remember to like the video if it was the case, subscribe to the channel, press the bell and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!